So last week we spent all of our time discussing and introducing data structures. So I had told you guys that there were, obviously we defined what data structures are. Hopefully we don't have to go through that again. And we discussed the first two of the data structures that we'll be covering in the course. They were arrays and queues. And so we had just stopped on stacks. Okay, so yeah, we learned about arrays and we learned a couple of things about each of the two data structures we covered, how to create them, how to access elements in them, how to manipulate them, so update the elements, change them, and when we use them. We also learned about what the internal representation of each of the data structures is in the computer, right? So we saw that arrays were like this contiguous thing of memory where everything's the same type. We learned a little bit about how to access them and how the computer uses them. Okay, and we also learned about queues. We won't go through it in detail again, but a queue was just what we call a FIFO structure: first in, first out. So the first thing into the queue, so in this case it was dog. We get, if you guys remember, we add things to a queue using this .enqueue command. So the first thing we added to the queue was dog, then we added 5, then we added cat. And when you say name.dequeue, it takes it out of the queue, right? But name.peek allows you to see it without removing it from the queue. So those were the two main ways that we could access and work with arrays, right? So we know a queue, sorry. So we know how to create a queue, we know how to manipulate a queue, like add to it by saying .enqueue. And we know how to access it by saying .dequeue or .peek. Okay, and we saw a couple of different examples about how those work differently. Okay, so yeah, whenever we need a FIFO structure, first in, first out, we would use a queue. One really good example of a FIFO structure is a messaging system, right? Like if you think about how WhatsApp handles messages, there's all of these messages coming, right? If we're talking about a group situation, it's two people could send a message very close together. So how do we manage that system? Well, as a message comes, it gets added to the queue, and the first messages that are added to the queue are the ones taken out of the queue. And there are a bunch of other examples you could think about where that kind of FIFO structure might be useful. Cool, and so that brings us to where we left off last week. So basically we had just finished queues. We had seen that there's all these different uses for a FIFO structure. We had experimented with it a little bit. But then what we wanted to think about is that there are other ways of doing this, right? So we've seen a FIFO structure in a queue, but what about a LIFO structure? So a queue, the first thing into the queue is the first thing to leave the queue. What if I want something where the last thing into the queue is the first thing out of the queue, right? And you can think about a few ways in which you would use this, right? So last week, you guys gave a few examples. It seemed like you immediately understood the concept, basically. Obviously, we still have to see how to create them and how things work on a more technical level. But you guys did immediately get it because one of you mentioned Minecraft stacks, right? So the first piece of dirt that you pick up in Minecraft gets added to your inventory, right? And it's at the bottom of the stack. You can continually pick up more and more and more things, right? More and more dirt. We'll just use that as an example. But whatever you're picking up, it gets added on the top of the stack. When you go and put it down, because you're building your house or castle or whatever, when you go put that piece of dirt down, the last one you picked up is the first one that you put down. Okay? If that example doesn't gel with you, a really good way to think about it is how pancakes work, right? A stack of pancakes. So if you make one pancake and you put it on the plate, okay, you make another pancake, you put it on the plate, make another pancake, you put it on the plate. The last pancake into the stack, right, that is the one at the top, is the first pancake out of the stack, right? First pancake that comes off of the stack. So we would call it last in, first out. Another way to think of it that's also quite topical, since it is winter, we're all wearing a lot of layers of clothes, right? You'll put on multiple layers. the last layer of clothing that you put on would be the first one that comes off. So this is how all of these things, and you could picture in a game, like if you have some kind of inventory management system and you need to layer the things, it will always be a stack, LIFO. We also saw one use of a LIFO structure back when we covered recursion, but we'll think about that a little bit more later. All right, so that's an introduction to stacks. That gets us to where we left off last week. And so, without further ado, let's just jump into us answering those questions we have about stacks, right? So we want to learn how to create them, how to add to them, how to or manipulate them, and how to access them to actually work with the things on the stack. All right, and then we also want to just we've already discussed when to use them, but we also want to see like an internal representation that the computer might keep. All right, so the first thing, obviously, when we want to create a stack is to, or when we want to use a stack, is to actually create the stack, right? And it's very simple. If you remember how we created a queue, it was like queue, the name of the queue, equals new queue. With this, it's very similar. It's stack, whatever the name of our stack should be, equals new stack, okay? And what that'll give us is just like a little line. Okay, you can think about the internal representation like this. Again, similar to queues, it might not literally look this way in the computer's memory, but this is a good way to think about it. There's like a foundation, okay, a place in memory that is the bottom of your stack. Okay, so in the computer's memory, the bottom of your stack is defined when you run this command. And the name that you give to the stack is what points to this bottom of the stack. So as we've been doing, I think we should actually just program this up in Rex Tester so that you can see that this is in fact how it works. Okay, like with queues, I am going to remove the generic here. Okay, so it says using system.collections.generic. I'm just going to remove it. So we import collections, all of the different collections. Okay. But you don't have to worry about that too much. It's just a little technical thing that you have to do if you want to use these things the way I want to use them here. And then we just say stack. Okay, stack. And you guys can give a name. If not, I'll just make up a name. Do you guys have any requests? I think we'll probably be putting our pancakes on the stack, right? That's how we'll probably be working things. Bob. You guys are so creative with namings. Everything's called Bob. Everything. Okay, I'm gonna call mine pancakes. If you program in Bob cakes. Okay, you know what? The creativity is worth it. Okay, Bob cakes it is. Stack Bob cakes equals new stack. Ah, someone came in as Brighter Futures. That's creative username. Okay, cool. So that creates our stack. And yeah, all that's going to do is give us like a place where we can add things to our stack. All right. So we've created a stack. Nothing particularly difficult there. Hopefully you guys are okay with that idea. Right. Very similar to how we could make a queue. Right. If I wanted to make it a queue, I could just say like queue Bob cakes equals new queue. Okay. Now I'm going to turn it back to a stack. This is where things get different, right? So with queues, how we added to a queue, we would say .enqueue, right? How we removed from a queue, we would say .dequeue, if you guys remember. Enqueue and dequeue. Obviously, when adding to a stack, we're not going to say enqueue. That wouldn't make sense, right? So obviously there's a different way. This is where things get very different. Okay. So, how do we add to a stack? Okay, there is a word, push. Okay, so you push something onto the stack. You push it onto the stack. So you'll say the name of the stack. We called ours Bob Cakes. Bob Cakes dot push, and then in brackets whatever you want to add to the stack. So you hypothetically what they added here was pancake 1. Right, pancake 1, and you could see that pancake 1 just fell down and it added to our stack. That's what the push command would do. Right, so you push things onto the stack. So let's do that with our stack now. And we'll obviously not add pancakes, we'll add bob cakes. Okay. So what I'm going to say is bob cakes, and remember C# is case sensitive. Okay, so it is capital P for push. And you can see it gives you a bunch of commands, and we want push. Okay, so it's like so. Okay, bobcakes.push. And now you can add whatever you want to your stack. And it's now remember this, when we were discussing arrays, we said arrays had to be homogeneous. Do you guys remember that? If you wanted to store, if you want an array, it has to be all ints or all strings or all doubles. Everything in the array must be the same so that we know the size of everything, right? Stacks, just like queues, can have different things. They don't have to be homogeneous. Anything's okay. So what I'm going to add to my stack is when I try to use stacks. So Saham, when it says up here using system.collections, yours will say system.collections.generic. So just remove that generic, and then you'll be using the same stack that I'm using. Okay. So it's a little weird thing. And don't worry about this weird arrow thing that they've got there. You see it says stack, and then it wants a T, so it wants you to give it a type. We'll see that next. We'll be discussing linked lists, and we'll see what they expect you to do with that then. I just wanted you guys for now to focus on the idea of stacks and queues rather than on like those little technicalities. But we will see what this is, what that is asking for in a bit. So don't worry, we're not running away from that, but we will. But we'll only see it later. Okay. So bobcakes.push bobcake1. Okay, so when I run that, there's no errors. C# knows what's going on, and we can also visualize, right? So what just happened? I said bobcakes.push bobcake1, and it added bobcake1 to the stack, kind of like what happened here. And obviously, I could add another one, right? I could add another bobcake, okay? And it will just go on top. Think about it like a stack. Do picture it like this in your head, okay? The next thing that I push onto the stack will like be on top of the previous thing. So if I couldn't get to the bottom thing, is the main thing that you must understand. The last thing I put on is at the top, so I'd have to take that off first, right? So let's do that in our example as well. So I'm gonna say bobcakes.push. Okay, and obviously this is going to be bobcake2. And obviously you could be adding any strings. Okay, you could be adding numbers as well. Whatever you liked, really. It doesn't matter. I'm just doing this one as an example. All right. And yeah, the main thing is that you understand the concept of a stack, not all the sort of nitty gritty. Okay. And we could add another thing to the stack. So you see we've now got 3, in this case pancakes, in our case bobcakes, onto the stack. So I'm going to go ahead and just add another one. You guys shouldn't do this. You should write out every line of code so that it gets into your head. I'm just going to cheat a little bit and copy paste and just change the 2 to the 3. Okay, so now we add bobcake1, bobcake2, bobcake3. And remember, so it's like, yeah, the order that you type in, don't picture it in that order, right? Bobcake3 is at the top of the stack. The last thing I added is at the top of the stack, right? It makes sense. Same as when you make pancakes. All right, cool. So we've seen how to add things to the stack, and it makes sense, right? You could just keep adding things to the stack if you wanted. But eventually we'll want to actually, eat the pancakes, or I don't know what you would do with bobcake, whatever. But you eventually you'll want to actually take things off of the stack and actually work with the stack, right? So we need to figure out that next question. How do we access and manipulate? How do we access the stack? How do we actually work with the items that we have on the stack? Okay, and so one of the commands you should recognize. Okay, so there's 2 of them, pop and peek. Okay, pop and peek. All right, Yeah, peak you should recognize from queues, right? Peak you should recognize from queues. So remember, if you peak in a queue, it will just show you what's at the front of the queue, right? It'll just tell you what's at the front of the queue. It's not going to remove it from the queue. If you want to remove it from the queue, you have to use, can anyone tell me? What if I want to see the thing at the front of the queue and remove it? What command would I use? DQ, exactly. So the thing, if I just want to see the thing at the front of the queue, then I would just say peak. Yeah, it's okay. Rex Tester would correct you anyway, right? If I just wanted to see the thing at the front of the queue, we would say DQ. And if I wanted to, if I just wanted to see the thing at the front of the queue, I would say peak. If I wanted to see and remove it from the queue, I would say DQ. And it's the same with stacks here, guys, or similar. Okay, if we want to see the thing that is on the top of the stack, so I just want to look at pancake 3 currently, then I would say the name of the stack dot peak, and it's just going to show me pancake 3. Okay. However, if I say the name of the stack dot pop, what it's going to do is show me pancake 3, and then like take it off the stack like that. Okay. So pop will actually take off the top thing of the stack. Pops it off the stack. Okay, you guys understand? Pops it off the stack. So we can see that let's actually see what happens here. Okay, so we've pushed 3 things onto the stack here. All right. If I say console dot write line, okay, console dot write line, and I'm gonna say bobcakes dot peak. Okay, bobcakes dot peak. And I'm going to do that twice, all right? You've seen this trick before. It's a good way for us to understand the difference between peak and pop, but also peak and DQ. Okay, so we're going to say bobcakes dot peak again on the second line, all right? So guys, this will print out 2 lines, right? It's going to print out 2 lines. What will those 2 lines be? Bobcake 1 and then, you say bobcake 1 and 2. Is that correct? Yeah. Let's think about this. So how is the stack working? When I peak, I see the thing at the top of the stack, Yuvia. I see the thing at the top of the stack. Okay, Saham says bobcake 1. Interesting. Remember, guys, you must visualize it. So Saham, you agree that bobcake 1 is the first thing I added to the stack, right? Bobcake 1 was the first thing that I added to the stack. So is peak going to show me that? You say 3 and 2. Okay, interesting. But remember, peak isn't going to remove anything from the queue. Peak won't remove anything from the queue, will it? You're hedging your bets now. You can't bet both sides. Why would it show me the beginning and the end? Remember, guys, so the last thing into the queue, onto the stack. The last thing onto the stack was bobcake 3. Would be the first thing off of the stack. Okay, LIFO. So stacks are LIFO. Last in, first out. Okay, so bobcake 3 was the last thing that I added to the stack. Okay, so when I run peak, it is going to show me. Yeah, you see. So you guys must be careful because I know this way it looks like the stack is going down, right? 1, 2, 3. But you must remember that it's actually like this. Okay, you must visualize it like this. The top of the stack, right? So it's like we made bobcake 1. We made bobcake 1, and then we added it to the stack. We made bobcake 2, and then we added it to the stack. But you see now 2 would be on top of 1. Okay. We then made bobcake 3, and we added it to the stack. So 3 would be at the top of the stack. Okay. So when we peak, we're going to see the top of the stack. All right. And remember, peek means that we don't remove it from the stack. We leave the stack alone. All peek is going to do is show us the top of the stack. So what this is going to do is print out bobcake3 twice. You see that? Bobcake3, bobcake3. Because I was just peeking. Right? I just peeked at the top of the stack. All right. Do you guys understand? Are you comfortable with that idea so far? So peek, however many times, peek will just show me whatever's at the top of the stack. Okay. Exactly like with queues, right? A queue, if I run peek, peek will just show me whatever's at the front of the queue. It's not going to change the queue at all. Nothing will leave the queue. It will just show me what's at the front of the queue. Okay. In the case of stacks, peek will just show me what's on the top of the stack. Okay. Awesome. So Saham gets it. Cool. If anyone's still worried about like peek, then do say, and we can see a few more. Okay. But cool. So we've got peek. All right. Now, what happens when I run pop instead? So the first command is going to be pop. Okay, pop. So the difference was, if I run peek, we see the thing at the top of the stack and we leave the stack alone. So after peek, it would return. Yeah. Good thinking, Yuvia. You're correct. So cool. Saham 2. Good stuff, guys. So if you look at this stack, let's see what would actually be happening here. When I ran peek, we saw that we just saw, in our case, it was bobcake. We saw bobcake3. And when I ran peek again, we would see bobcake3. Okay, so you guys are happy with that. And we wouldn't have touched this stack either time. The stack would look exactly the same after running peek twice. Now, what's the difference if I run pop the first time? Then what will happen is pop will show me pancake3 or bobcake3, and then it's going to remove bobcake3 from the stack. And when I peek, the new top of the stack is bobcake2, right? So we expect it to go bobcake3 and then bobcake2. Now remember, this second time, right, on this line when I run peek, the stack will not change, right, on that line. So it will still have now bobcake1 and bobcake2 after this line. So if I ran peek again, it would give me bobcake2 still, right? So I'm only running pop once is what you must remember. So what will happen? We'll get bobcake3, bobcake2. Okay. All right. Makes sense, right? Cool. So what we've done here is we've basically said we've made a bobcake, we added it to the stack, we made another one, we added it to the stack, we made another one, we added it to the stack. Okay, so we had 3 bobcakes on the stack. We then decided just immediately to eat the first bobcake, so there were only 2 left on our stack. Okay, and we just looked at the next one. Okay, we just looked at the next one. We didn't eat it yet, so there's still with the peek command. We just looked at the next one on the stack, but there's still 2 things on the stack. We were just considering whether or not we wanted to eat that one as well. Okay, but now, and this is where things can get somewhat confusing, but remember that there's only these 3 commands really that you have to worry about, right? Push, pop, and peek. If you know what each of them do, then you'll be able to understand what the stack is doing, right? So what if I add another thing to the stack, right? I could do that. So we made 3 pancakes. I ate one of the pancakes, and then I made another pancake and added it to the top of the stack. So it looks like this. Pancake 1, pancake 2. It was pancake 3, but I ate pancake 3, made another pancake, and put it on the top of the stack. And we could do that here as well. How would I add another bobcake to our stack, guys? How would I add another bobcake after this pop peek thing? What command will I use to add another bobcake to the stack? Remember, there's only exactly. So we'll say bobcakes dot push, right? And we'll say this time it's bobcake4. All right. So now when I say console.writeLine, and I'm going to say bobcakes.peak, so I'm just going to look at what pancake is at the top of the stack. It's going to say bobcake3, okay, because that's what was at the top that's the one that I ate with the .pop command. I then peeked, and you could see that bobcake2 was on the top of the stack. We then went ahead and made another bobcake4, okay, and then I checked the stack after we made bobcake4 to make sure that bobcake4 was what was on the stack, okay. And so the stack that we would currently have here at the end of all of these operations would look like this. We would have bobcake4 on top of bobcake2 on top of bobcake1, okay. And that's stacks, guys. It's not too bad, right? Are you guys comfortable with stacks? Yeah, cool. So yeah, it's all you have to worry about. This is how we remove the thing from the stack is pop. Peek will just show you what's ever at the top of the stack, and push will actually add something to the stack. Okay, that's what you need to know about stacks. It's not too bad. And the easy way to remember it is this little acronym. Okay, stacks are LIFO. LIFO, that's what a stack is. Last in, first out. And a queue is FIFO. First in, first out. Okay, LIFO and FIFO data structures. All right. Cool, so that is the end of stacks. We made it through that quite quickly, actually, which is cool. Awesome. Link, yes, or link. Next is what's something called a linked list. Now, when like a computer scientist or a programmer says list, this is what they mean, okay? What we'll be learning now. Arrays are something different. We know what arrays are, okay? But arrays and lists are different concepts, okay? So we'll now learn what a list is. But yeah, the technical name is called a linked list, okay? Yeah, exactly. Instead of arrays, you should usually say collections. That's correct. But I mean, instead of lists, if you want to not call it an array, then call it a collection. That's correct. But yeah, now we're talking about linked list. All right. So the first thing I want to explain is why does a linked list exist, and like what problem is it solving? Okay, because you've seen a couple of things now, right? You've seen stacks, which are LIFO structures, and it kind of makes sense why you would want a stack, right? There's a bunch of cases where a stack would be useful, okay, and we've discussed some of them. You've seen queues, a FIFO structure, and there's a bunch of cases where you would want to use a queue for something, right? You can think of lots of examples in the real world where queues would be useful. And then you've seen arrays, which is like just a general way of holding a collection of items, right? So why would we need another thing? Why are there so many of these? What would a linked list possibly be doing? So that's the first thing that I want us to understand. Okay. So why do we have linked lists? Okay, in order to find out why we have linked lists, we have to go back and think about arrays just a little bit, just quickly. So we'll discuss arrays until we take the break, and then when we come back, we'll finish off by discussing linked lists. Okay, so we remember this is what an array would look like, right? Here we've got an array with 4 integers in it, 5, 6, 3, and 4. Okay. Cool. What I want you to remember, an integer is, okay, how many bytes is an integer? Can someone tell me? How many bytes is an integer? In C#. Mostly. There are a bunch of other Okay, you say 32. Is it 32? Ah, yeah, there we go, there we go. So, and now I can ask, how many bits is an integer? How many bits is an integer? 32. Okay, cool. We're all on point then. Or at least we're all at the same place now. Cool. So yeah, an integer is 32 bits. Okay. Now when I have an array, remember when we create an array, we have to either give C# the entire array, like you have to give it 5, 6, 3, and 4, and say I want this all in an array, or you have to give it a size, right? You have to say I want an array that can hold 4 integers. Okay. Why do we have to do that? Well, it has to do with how C# organizes arrays, right? So when we say we want to access position 0 in the array, right? When we want to access position 0 in the array, then C# will say 0 times 32. And that gives me this place in memory, right? So it's accessing the 0th bit in the array, right? When I want to access position 1 in the array, we'll say 1 times 32. So it goes into memory and it says, okay, the array starts here, and I need to go forward 32 bits, and then I'll get to the second integer. Okay. When I want to access position 2 in the array, we'll say, okay, I want to access position 2. So what C# will do is it'll say 2 times by the size of an integer is 32 bits, and it's going to go, okay, here's position 0 in the array, the 0th bit. This is the 32nd bit. This is the 64th bit. And then it would know that, okay, these next 32 bits are the third, but like the second index in the array. Okay. So this is why we start counting at 0, if you guys understand. Right? So it has to do with how we're accessing the array. And when we want to access the next part of the array, which would be index 3, we would say 3 times by 32, and we would go ahead and access that part of the array, okay, the 96th bit. Okay, so that's how it would work with 4 integers, and you could just scale it up. If you were storing 100 integers, you can find the 87th integer easy, right? You would say like 86 times by 32, and you access that specific bit, and the bits after that are the integer. Don't worry too much. I know that's super technical, but this is, I do want you guys to get an idea of why linked lists exist. Okay, so hopefully you can kind of follow what's going on there. Okay. Now, I also want you guys to remember is that obviously there's a lot happening in the computer's memory, right? We've got our little array of 4 integers, but over here we don't know what this red space in memory is. Okay, we don't know what's there. Could be something super important, all right? But the computer is not going to let us access this. And we don't know what comes after our array in memory. But likewise, the computer's not going to let us access that. Okay? So we've got this little piece of memory to work with, and that's what the computer gives us. All right. Cool. Now, what I want to ask you is how would you add another thing to this array? Right? So, what you could say, hypothetically, right? So this bit of memory is taken by something, this bit of memory is taken by something, and I say, actually, you know what? I don't want 4 integers here anymore. I want 5 integers. I want 5 integers. Okay, what if I want to store 5 integers? You could say like, oh, well, couldn't, you could ask, maybe one of you would suggest, why don't I put it there? Okay, just at the end there. That's my 4th integer. I've added another 4 to the array. But you guys can see this red space here. Not only do I not know what's in it, I also don't know how large it is. Okay, so I can't say, you can see our indexing would be broken. Our indexing would be broken. How would you access this integer? Okay, you couldn't. So arrays can't work like this. In order to add, so to make our array go from 4 elements to 5 elements, or 4 items to 5 items, we would have to create an entire new array and copy all the old elements across and then add our 4. Okay. That's the only way to do it. So it's very inefficient. You can see that we wouldn't want to use an array in this case, right? We would have to create a whole new array. We would have to move to a whole different place in memory and copy across these 4 things. Okay. The other thing is that the array will have a fixed size regardless of how much of that space we actually use, right? So if you want the array to hold 100 elements, or you want it to be able to hold 100 elements, when you create the array, you have to create it as if it's holding 100 elements. So it reserves 100 times 32, okay, so 3,200 bits in memory to hold 100 integers, okay? But what if you just put 5 integers there? It doesn't matter. All of those bits are still taken for your array, okay? So that's another silly thing about arrays. So you can see that arrays are very useful, and we've used them before, and you could see why you would want them. But they're not perfect in every situation. And that's where linked lists come in. Okay, that's where linked lists come in. So we are a little bit early because we are making very good progress. But I think let's just take a break now. So we'll do a 10-minute break and come back at 15:50. Okay, 15:50. Because I think this is a good place to break, because it won't break the idea, rather than stopping in the middle of our discussion and learning of linked lists. I'm going to stop now. Okay, so yeah, we'll come back here. So yeah, you can go get some water or anything, and I'm going to go get some water, I think. And I'll see you guys at 15:50. Yeah, that's another way to pass the time, is scribbling on the shared screen. Yo, you guys have been busy. It actually makes my computer lag. Is that the annotate button? No, it's not. There it is. Okay, can now see the chat again. That's good. Oof. Cool. Freezing, freezing, freezing winter. How do we turn that thing back on? Ooh, in our last bit of break, I did want to ask how's school, guys? I think because Roosevelt is giving us huge trouble, with scheduling, but you guys haven't. It sucks. Yeah, okay, that's fair enough, I guess. um, Tough. It's a lot of work. Yeah, I can imagine. But I think Bryanston has handled it better than the other schools. I know it might not feel like it to you guys, but oh wait, so you guys? Oh right, yeah. I didn't know that much. So you guys are going back to school very often. Some of you say we're still at home. I don't know. I guess it depends on your grade, right? Depends what grade you're in, whether or not you're. Yeah. Okay, makes sense. Grade 8 at home. Okay, cool. Yeah, I really wonder how they're actually going to handle this. What sense do you guys get? Like, do you think that that they'll actually manage to finish? That you'll write your tests as usual and like go on to the next grade next year? Is that what you think will happen? Jeez, that is a big circle.
It's gonna open for 3 weeks and then leave.
Okay. And you think that'll be it for the year? Yeah, I don't know. They sent a schedule. Okay, cool. Yeah, I think it's a difficult situation though. I do wonder if they'll manage to finish and stuff. Especially finishing for all the grades. Ooh, turn that off. Shut down schools is trending on Twitter. Okay. I suppose I think a lot of people feel that it is a little bit dangerous to, yeah, you guys are going to give me epilepsy with all this appearing and disappearing circles. Okay. Anyway, so I think shut down schools is, yeah. What do you think, Joshua? Do you want schools to shut down? All of you. What do you think? You do. Okay. Yeah, I mean, I agree. I think it is a little bit crazy to be trying to salvage the situation. But I can imagine. Can you imagine for those expensive private schools though?
Bryanston is trying too hard.
No, all the schools are doing it though. Like Roosevelt has a crazy schedule at the moment. So does Crawford. I think it's a tough situation. But you can imagine like if it's a super expensive private school like a Michael House or something. Really wonder, because will the parents be willing to pay fees for like an extra year, and will they have to give discounts? Although I guess all schools will be having problems like this. Anyway, okay, so enough scribbling, enough chatting. Let's get back onto this. Okay, linked lists, pretty challenging concept, and yeah, so this is a big topic in first year computer science. Okay, so what I want you to remember, what problem are we solving? The problem we're solving is that arrays in C# have a fixed size, and that size cannot be changed easily, right? So let me remind you about that. Okay, I'm gonna throw away our stacks for now. Let me go ahead and refresh actually. Okay, so I'm refreshing to get the generic back for when we start working with linked lists. Okay, so what I want to show you, I just want to remind you to create an array. We would say something like int, these square brackets, and we would say the name of the arrays. So say numbers. We want 5, 6, 3, 4, and we would say something like equals 5, 6, 3, 4. Okay, and then close the line. Okay, so what that'll do is create an integer with those create an array of integers with those 4 numbers. Okay, you guys are comfortable with that idea, hopefully. And you know that the other way of doing this is to say like maybe int nums equals new int, and then specifying a size. Okay, so this will be an empty array that can hold 4 integers, but currently it would just be like I can show you. Let me just show you. So I'm going to access nums in position 0. So this is that empty array. You can see it made it 0. And if I access nums 1, it's 0. If I access nums 2, you guys can hopefully see the pattern by now. If I access nums 3, okay, so when I create an integer like this, it just creates an array that holds 4 integers and just makes all of them 0. Okay, so you can create it in these 2 ways. But what I want to remind you guys of is that I can't now change the size of the array, right? If I say nums in position 4, it will break. It's going to take a while to break because it is Rex Tester, but you can see, there you go, it broke, right? It broke. Exception in user code, index out of range exception. So in order to hold 5 things in the nums, in the nums array, I would have to change this to a 5, and now it would be okay. All right. If I wanted to hold 6 things, I would have to change it to a 6. But the point is the array has a fixed size, right? That's what we're trying to get around. It's very difficult to change the size of the array because of the way it works in memory. Okay, that's what the linked list is trying to address. So what I want to show you is how we're going to take this exact array here, this 5, 6, 3, 4, okay? And remember the problem we ran into on the last slide, if I wanted to add another 4, so I have this array that holds 5, 6, 3, 4. If I want to add another 4, you could see that I can't do it with this array, right? I would have to create a new array that can hold 5 things. Okay? I have to create a new array that can hold 5 things. So the array didn't work for this. So what we're going to do is say we have this array, okay, 5, 6, 3, 4. What we're going to do is put it into a linked list and see when I want to add that extra 4, how does the linked list help us? How does a linked list help us? Okay. So, yeah, let's start this. Can be quite hectic, but hopefully you guys will get it. So, how does it work? You have this little arrow, okay, this little arrow, a pointer, if you like, and it's just pointing to something. For now, we'll just make it null. So what you must think about this as, there's an empty place in memory, okay, that we can point to. Empty place in memory that we can point to. Hopefully we're comfortable with that idea. So what we're trying to do is to take this array that we have here, 5, 6, 3, 4, and represent it in a linked list. And then we'll see how that helps us. Okay. We're going to call this pointer the head of our list. The head of our list. You can imagine it as almost a sort of snake, if you want. Okay, but we've got the head of our list. And by the way, you guys can follow along with this on page 74. Hey? So this is what would happen when we run this command. All right, create linked list. Okay, so create linked list that can hold integers. We'll give it a name equals new linked list ints. So, Saham, as to your question, because you were obviously programming along with the stacks. So back here we are now importing generic again. Okay, so we say using system.collections.generic. Okay, we're back to generic, and yeah, so we'll do that, and now we are going to create a linked list. Now, you guys remember, I'm just gonna show you how we did the previous ones. So to create a queue, we said queue, the name of our queue, like name of queue equals new queue, right? We would say something like that. To create a stack, we would say stack name of stack equals new stack. Okay, so that's how we did that. So I'm sure what you guys are probably hoping, and what would be nice, is if we could just go, all right, linked list list equals new linked list, right? That would be great. And it is almost like that, but the reason we don't do it this way is because of the error that Soham brought up earlier. Okay, linked lists as created in C# are homogeneous. Okay, remember when we were discussing arrays, we said that they were homogeneous. They hold one type, right? So you have to tell the linked list what type it is holding. All right. So how we do that is we say, we put these two little arrows, so a left-facing arrow and a right-facing arrow. On most keyboards, you'll find them next to the M key, like on the right of the M key. And you just type whatever type the linked list is holding there. And you can use whatever type you want. So we're using int, obviously, just to keep things simple. But you could say string, or you could say double, or boolean, or long, or short. You know, whatever types you guys know, you could use those. Okay. We're just going to use ints though, just because it makes sense. All right. And so that's okay. Sorry, that's errors for the queues and stacks, because those are the errors Saham would have gotten earlier. We're now using generic, so our stacks and queues also require a type. But what I want to show you guys is it's exactly the same as this, all right? Exactly the same as this. So instead, you would just say queue, the type that the queue is going to hold, the name of the queue. What did we call our queue again? I think we called it Bob as well. Equals new queue. And then just say that it's holding an int, and you put the two normal brackets after it. Okay, so the only difference is that things would now require types. Okay, not a huge deal. It's just a problem with the generic versions of these. Okay. But yeah, so we're talking about linked lists. Linked lists are holding a particular type. In this case, our linked list is holding an int, and you can see whatever the type that your linked list is holding is by looking inside these arrow signs. Okay, are you guys comfortable with that? I didn't know how weird this idea was. You guys don't mind that? It is a slightly different place to specify. You have seen iComparable being used like this, right? It's similar to what was happening with iComparable. Okay, Yuvira's okay. If anyone's worried about that sort of idea, feel free to ask. But yeah, you just specify the type in between these two arrows after the thing you're creating. Not too bad, I think. Awesome. All right. So, cool. So what we've done when we created this was to just say, all right, we've got this thing here. We've got a head that is pointing somewhere. Okay, and that's just what we call it. So that we're pointing at a specific location in memory. That's all this list thing is doing, and we could call it something else. You guys would probably recommend something like Bob list. So I'll go with that. Okay, we've got a Bob list. So it's just pointing to a specific place in memory. At least that's how you should picture it. Okay. So what we're going to do is create like a node structure. Okay, a node structure. So each sort of node in our list is going to have two things. Okay, so we've got this thing that's pointing to a specific place in memory. We're going to replace that empty place in memory with a node. Okay, like that. So it's going to look like that. All right. The node is going to have two things. It's going to have the thing that it is storing. Okay, in this case a 5, because that's the first thing in our array. And the second thing that node holds will be another pointer to a place in memory. Okay. So it looks confusing. How it's done in code is very simple. But that is what's happening. That's the internal representation. So remember, one of the questions was about each of our data structures was understanding how the computer is representing it. So this is how a linked list differs from an array. Okay. So how we do that is with this command, add last. Add last. So you'll say the name of the linked list dot add last and then the item that you are adding. Okay. And that will create a node like this. And the node will have the thing that it is storing, the item that you added, and a pointer to another part of memory. Okay. So let's just start with that. All right. So I'm just going to show you just to see that it works. Don't worry, we're going to spend a lot of time with this. Okay. And you can see there are a lot of different things if you're typing along in Rex Tester. You'll see there's a lot of different things. You can say add first, add before, add after. All we care about for now is add last. Okay, add last. Okay, and we're specifying a integer value. So we just say 5. In our case, just 5. Because our linked list is holding integers, right? Add last 5. Okay, and when I run this, let's just make sure that nothing's typed incorrectly. You can see it runs. So C sharp's happy. Okay. So all this did was add this kind of thing to our linked list. Okay. Now, so you've seen this command add last now, and you can probably imagine that you can call it multiple times, right? It's the same as any other command. So you could now, we've just added 5, but you could add 6. Okay. So what would happen? If I say add last 6, what happens? You can see that empty place in memory is replaced with another node. All right. The node has two things. It has the number, the item that I am storing, 6 was the next one we wanted to add, and it has a pointer to another part of memory. Okay. So, and you could picture, we could add another thing, right? Where this thing is pointing, I could replace this with another node, 3. Right? Happy with that? And where this pointer is pointing, I could add another node, right? 4. Okay. Right. Might seem a bit strange so far, but don't worry, we'll explore it more. So let's see. Yeah, I think it's because someone was turning on their mic. It's not... All right. So let's do that ourselves. So we are adding 5, 6, 3, and 4. Okay, Bob list dot add last 6, and then 3 and 4. Bob list dot add last. Ooh, I left out the dot. Bob list dot add last. All right. So what we have done there is we've created this structure. Cool. So you might see how to create it and still be a little bit confused about what this is allowing us to do. Okay. So I do want to spend a little bit more time on that just so that you guys understand. All right. Remember how we accessed things in an array. Right. So I just want to jump back to that quickly. How we access these things in the array. They were all next to each other, right? They were all next to each other in memory. So the way I could find where one was to say, okay, the array starts here. Okay, the array starts here. I know what part of the array I am looking for, right? I might be looking for the second part or the third part or the first part, right? I know what part of the array I am looking for. I know how many bits an integer is. And so I can find wherever in the whatever I am looking for in the array by just saying, I know where the start is. Let's say I'm accessing position 2. The array starts here. 2 times 32 is 64 bits. So I go over. That's 32 bits. That's 64 bits. All right, cool. This is what I was looking for when I was accessing position 2 in the array. I was looking for the 3. Okay. So in order for this to work, the array had to be, guys, when something is next to other things in memory, what did we call that? Do you guys remember the word? It was a long word. Don't worry about spelling. Do you guys remember the word we were using? Ah, Connor has load shedding. That's a pity. Do you guys remember what word it was where everything was next to each other? Can you guys define an array? Define what an array is. Do you remember? There were 2 new words we learned when we created an array. I'll give you the one. The one word was homogeneous, okay, which meant that everything was the same type. Yeah, that's correct, yeah. So, the word was contiguous. Contiguous. So the array, everything is next to each other. Okay? And you can see that our problem with the array is that when I want to make it larger, the memory, all the contiguous memory is taken up or could be taken up, right? All of the contiguous memory could be taken up. So when I want to make the array larger, I have to move everything to another part of memory that has enough space. Okay? So what the linked list solves is it goes, all right, these things no longer have to be contiguous. Okay? Remember, our head, the head of the linked list, points to a place in memory, right? It points to a place in memory. The head of the linked list points to a place in memory. So when so it can be anywhere in the computer, right? We have this thing that points to a specific place in memory. That place in memory can be anywhere in the computer's memory. And every single part of our list has a pointer that can also point anywhere in memory. So what this means is that the items in the list do not have to be contiguous like they have to be with the array. Okay, it's a bit of a complicated idea, so I do want you guys to, I don't know, suggest to me when you get it. Okay, so the array, everything had to be next to each other, right? But now we point to specific parts in memory, and so we can like jump around. Okay, so like I know where 5 is. Right, I know where 5 is. I can always find 6, right? Because 5, this item 5 is inside a node that points to 6. So if I know where 5 is, I know where 6 is. And if I know where 6 is, I know where 3 is. If I know where 3 is, I know where 4 is. Okay. And then I know how to add another thing to the list. All right. Because I can follow this chain throughout memory. Okay, are we kind of getting that? Are you? So every single node actually stores a pointer to the next one, as opposed to where we had arrays where everything had to be next to each other, and so you had to access in like that. In order to be able to access it, it had to be next to the other parts of the array. Whereas with the linked list, as long as you can always access these things sequentially. Okay. Do you guys understand? Shall we see another? Let me show you in another way. Actually, yeah, I can annotate. All right. Let's try this. Oh, wait, I can't move it when I'm annotating. All right, interesting. All right, let's try explain it this way. Okay, so if I have an array, all right, is there a way I can draw shapes or something? That would be helpful. Oh, that's nice. Where do I get that? I can't find it. Select mouse text draw. Oh, right, cool. Awesome. Okay, so we have something like this, all right? This is our array. Okay. What I'm going to say, okay, the computer has a lot of memory, and the memory is measured in bits, right? Actually, I should maybe make it white so that I can draw on it more easily. So let's do that. We're going a little bit impromptu. So I'm going to say draw. Ooh, this one might work even better, actually. Let's try that. Oh, no. Okay, that doesn't work at all. What even is that for? Oh, of course white won't show in the background. Okay, a light color. There we go. Cool. Some growing pains, but I think I've figured it out. Cool, let's think about this. Okay, so I have an array here. Okay, all of the items in this array are next to each other. All right, they're next to each other. So let's say I'm going to make it so that this array is holding, okay, so that's 1 item, 2 items, 3 items. Okay, we are Drawing with this thing is very difficult, actually. All right. So we've got 1, 2, 3, 4, 5, 6, 7 items in our array. Right? You can see that they all have to be next to each other. Why? Well, because the computer, when it creates the array, what it's doing is saying, all right, I know where the array starts in memory. Right? The computer has a lot of things in memory. It's doing a lot of stuff at once, right? It has a lot of stuff to remember. Okay? It has to know your browser is somewhere in memory. Like, I don't know, if you have a game open or Word documents or anything open, Zoom, all of those things are in different parts of memory, right? Like the whole operating system is taking up some memory. And so when you create an array, it's saying like, okay, this array, it finds some space for it, okay? And you know how much space it needs because you told it how many integers you're holding, okay? And so it says, all right, let's say it says we'll just pick a silly example. We'll say the 30th bit in memory is free for your array. Okay, the 30th bit. Okay, so the first 30 bits are busy. They have something. Let's say the first 30 bits of our memory are running Zoom. Obviously a bit unrealistic, but let's say that. Okay, the first 30 bits of our memory are running Zoom. Okay, after that, and you know, it's not necessarily all, in order. Memory is very messy. There could be a bunch of other memory of the computer that is taken up by other stuff, right? It's all busy. The computer managed to find this one space where we are using 1, 2, 3, 4, 5, 6, 7. So 7 times by 32. Not even going to try. 224 bits. Okay, 224 bits. So the computer went ahead and reserved 224 bits for our array. Okay, we'll end at 430 because we started at 3. So, but yeah, I want to get through this idea of linked lists. Okay, so wait, where did my mouse go? There it is. All right. So the computer reserved 224 bits. I think I probably have to expand my slides on linked lists a bit. Okay, 224 bits. Each bit is 30, each integer. Okay, so we're storing 7 integers, right? 1, 2, 3, 4, 5, 6, 7 integers, which is 224 bits. Each one takes up 32 bits. 32 bits. Okay. How does the computer, if I want to, and we know how it's labeled, right? This is position 0, 1, 2, 3, 4. Yo, guys, we're all big on the annotations, and now that I need your assistance, there we go, Saham, that's good. Yeah, let's finish that labeling. All right, so we've got multiple positions here, right? 7 integers, okay? And we access them like this. How does the computer actually access it? It goes, okay, this array is in the 30th bit of memory. That's where it starts. So it goes there. And when it goes there, it arrives here, right? It arrives here. Okay, I can actually show this to you. Let's do that. So in these last few minutes, let's just really understand what the array is doing here. Okay, don't worry, we will come back to this little example here. Okay, so what is happening here? We created a list of numbers. Int numbers equals new int, and it held 7 things. Okay, 7 things. So the computer has created exactly this. If I want to access the 3rd thing, or rather the 4th integer in this list, okay, I would go 0, 1, 2, 3. I need to access position 3. I'll say numbers in position 3. Okay, how will the computer go and fetch numbers in position 3? What it'll do is it'll go to, let's say the array was stored at the 30th bit, right? So it'll go here, it'll find this, the start of my array. You see I gave it the number, right? I gave it the number, which was 3. Ooh, 32, Saham. But yeah, exactly. It'll say 32, because that's the size of the integer, times by 3. Okay. 32 times by 3, which will bring me, which is not the specific part of memory. Like the array starts at 30, right? The array starts at 30. So we'll say 32 times by 3 plus 30. Okay. Plus 30. And that'll bring me specifically to this position. In all the computer's memory, this position uniquely identifies my integer. Okay. And you can picture this because there are gigabytes in your computer, right? Thousands and thousands, millions of bits. Okay. And this is how the computer is organizing things when we come to an array. Okay. But you see, in order, the main thing you must take away from this is not the technicality of the maths. You won't be asked that. What you must take away from this is that clearly for that to work, all of the items in your array have to be next to each other. And so with a linked list, what we do instead, and hopefully we can get through this idea in the next little bit, is we say, instead of storing everything next to each other, what we're going to do is so we store that position, the start of our linked list, exactly like with the array. We store the start. Oh, let me erase that. Okay. We store the start of our linked list. Actually, we can use the slide for this. Okay. We store the start of our linked list. But every single item in our linked list stores a way to find the place in memory of the next one. So you know we were using that mathematical way, going like 3 times 32 to find the next part of the array, or 4 times 32 to find the fourth item in the array, or the fifth item in the array. So we use that mathematical way of finding it. Instead of doing that, every single thing in our array will just store a pointer to a specific place in memory. So what that means, like this guy could be stored in place, this guy could be stored in place 32, right? This guy could be stored in place 32. Okay. And the 6 could be stored in place, whatever, 890. Okay. And the next thing could be stored in place 3000, whatever. They can all literally be anywhere. Anywhere in the computer's memory. Anywhere you liked. Okay, crazy memory addresses. But the important thing to get is that this little pointer here, that little arrow, is what's pointing from this place in memory to that place in memory. So you can always like snake through memory. So you can get from one place to the next place, to the next place, to the next place. I am trying to... Are you guys getting it more? Yeah, exactly. So the head points to the first position of the array. Let's say that was at memory location 32, right? 32. Okay, that's what the head points to. Each node has another pointer, right? So there's this pointer that points to this place in memory. Each node has a thing that points to another place in memory. Okay, and another place and another place. Okay, so you can jump through, you can snake through memory like this. Okay, and yeah, it can go backwards, it can go forwards, wherever. You can put every item in its own place in memory. And as long as the previous item points to it, you'll always remember where it is. Do you guys understand that? I do know it is maybe a little bit weird thinking about it this way, but or thinking in this way, but this is how technical you have to get with computers. Okay, so Saham gets it. That's good. Does anyone have any question that can maybe set me on the track to why you aren't getting it, or are we all comfortable with this idea? So if I want to access position 3, let's see how the computer would do it. It's hidden from us when we actually use linked lists, but let's see how the computer would do it. it would say, all right, I know the start of the list because I have head. Okay, head is just what the linked list starts at. Okay, so it goes, all right, I know where that is. Okay, so it goes through. It says, all right, I've found the first item in the list. Right? It has this pointer now because it found the first item in the list. So it goes to the next item in the list. Okay, and it goes, all right, cool. So I've found the next item in the list. But remember, we said we were looking for 3. So we were looking for the third item in the list. We found the first one because head pointed to it. We found the second one because the pointer in head pointed to the second one. We're looking for the third one. Okay, the pointer inside the second one points to the third one. And so then there we go, we found it. Okay, so we didn't have to do any fancy multiplication or anything. In a way, it's easier to understand the technicalities of this than it is to understand the array, right? Because everything is just literally pointing to the next thing. Okay. So if we wanted to access the second thing in the list, how would we do it? We would go to head over here. What's the Hums pointing at? The node that head points to is the first thing, right? So this is the first thing. We were looking for the second thing. So the first node will store a pointer that points us to the second thing. And so there we go. We can immediately go find it. All right. So that's just how a linked list works inside the computer. I hope you guys get it. If you don't, please do ask. But yeah, I hope you understand. I don't think it's too bad, at least from what I can gather from the questions and stuff. But yeah, that's how we create a linked list, and this is what the internal representation looks like in the computer. Okay. Do you guys understand? Okay, cool. I'll take Saham's word for it that all of you guys get it. Right, now we do have 4 minutes left. So, cool. So let's see how we can actually go through this process. So let's jump back to C# quickly. Cool. So I'm going to say, well, let me go and erase these quickly. I think we might have to save this for next week because there are quite a few. So erase all that. And just delete this. And I'm going to quickly create another linked list. So I'll say linked list int bob list equals new linked list. Int. Okay, something like that. We'll say bob list dot add last. Okay, and we are just going to add 5. I'm going to add a few more things to the list. So we've added 5. I'm going to add 3 and 6 and 4. So those are the things in our list. All right. So what I'm going to say, I'm going to show you how you would actually do it. And understanding the internal representation might have been difficult, but getting this is actually, it's quite simple. You might be surprised even. Yeah, no, actually, I can show you it. We can show you it very literally. Hopefully that works. So I'm going to say console.writeLine bob list. Firstly, that probably errors out. Okay, cool. So look, it tells me this is a linked list. Okay, so that's what bob list is. This is the head. Okay, it's the head. Okay, bob list. So then I'm going to say bob list dot first. Okay, bob list dot first. Okay, you see now it says linked list node. So what is that giving us? The first thing in the linked list. Okay, it's giving us this. Okay, the whole thing. It's giving us the value and the pointer. So I can say boblist.first.value, and that's going to print out. Let's see. I know we are rushing a little bit. I think I will save it for next week. But let me see, actually. What do you think this will print out? So this is going to print out the value associated with the first node. What was the first thing I added to the list? Let's see. Does anyone know? What is the first value we added to the list? Good stuff. Yes. Okay. That makes me happy. So you see it prints out 5. And now what I want to show you, I'm just going to show you quickly. So we'll say boblist.first. Okay, so that's the first thing in the list. I'm going to say dot next. Okay, boblist.first.next. So what that is doing is saying boblist.first. So boblist is the head. First, so that gives me the first node. Next will follow this arrow to the second node. So now what if I say next dot value? Okay, now remember we added a 3 next rather than a 6. We should have done it in the correct order. So this was 5, 6, 3, 4. Okay. So it seems a bit difficult to follow. It might seem a bit difficult to follow. But what I want you guys to do is just actually think about it this way in your mind. So boblist, okay, gave us the head. Dot first gave us this node. Dot next brought us to this node. What will dot value give us? Dot value at this second node. What will that give us? And you'll see it gives us 6. Okay. And you could say dot next dot value gives us 3. Dot next dot value will give us 4. Okay, so you can see how you can jump between the nodes. You can jump from one node to the next. Okay, we are going, I think we have to, so we definitely will, spend more time with linked lists next lecture. So we'll spend the first half of the next lecture discussing linked lists. The second half of the lecture, hopefully we'll end up discussing sorting and some new stuff, and that'll bring us to the end of section 3. So we'll do that next week. But for now, we are done. Okay. So yeah, thank you guys for concentrating. Yeah, I know the linked lists, I thought it would be quite complicated. I didn't know just how much time to spend on it. So yeah, we'll spend more time on it next week and really, flesh out our understanding of linked lists. And then we'll, hopefully finish off chapter 3. That'll be good. Or section 3. Cool. So thank you guys. Let me finish recording. Yeah, thank you for coming in and see you next week.